that you just heard, but from the theoretical side, to talk about some of the simulations that we've done at Auburn involving these ultracold plasmas. I'm not going to really talk at all about some of the other simulations that have been done, but let me just mention a little bit about them right at the very beginning. There have been a couple of molecular dynamics simulations of this system performed by Stéphane Mazabé and Lee Collins, and another group with Tim O'Neill, whatever. And those simulations have been important because they're really not in disagreement with anything that I'm going to tell you. The problem with the molecular dynamics simulations, or the difficulties with them, is that they've been able to follow the plasma really for just like the first, in essence, few nanoseconds, or a few 5 or 10 nanoseconds of the plasma evolution. I'm going to look at the plasma in essence a much more crude way. I'm not going to do molecular dynamics and follow all the particles. But because of that, because of the approximations, I'll be able to get to much longer times and look at stuff in a much more interesting way, I think, because in some sense I can put stuff in and take it out by hand. Whereas if you're doing molecular dynamics simulation, you have everything in, which is a great thing, but you have everything in whether you want it or not, which is sometimes makes it tough for interpretation. My main collaborator on this is Jim Hansen, who is a plasma theorist at Auburn. He's right in the office next door to me. When I first would come in with these papers, I said, God, look, this is so exciting. They have these really strongly coupled plasmas. They have really cool stuff. Let's do something. Let's do something. And so finally I convinced him, in essence, to take me on as his graduate student. So now I sort of have like a stepfather kind of thing. And so I come in and do some stuff and show it to him, and he'd teach me a little plasma physics. And so none of this could have been done without him. He's a really great help. Another important thing was I talked quite a lot with the experimentalists involved with the various cold plasmas, the people at NIST, or used to be at NIST, Tom Gallagher, Phil Gould at Euler, talked with all these guys, and it really helped in my understanding of what was going on in these plasmas. So since probably, like me, a lot of you don't know what the important plasma parameters are, I put them on 2 slides. And I start from the very simple ones, like the temperature, and you probably know that the electrons and ions will have a temperature, they'll have a density. So those are obvious things. One that's maybe not 100% as obvious, it's a derived parameter, which is, in essence, you take the volume occupied by one electron and convert it into a length. And so that length, for example, for a 10 to the 9 per cubic centimeter density is about 6 microns, whereas the size of the plasmas are a few hundred microns or so. Now, what you can also do with this distance, in essence, between the particles is use it to imagine that that is controlling like a potential energy. As Tom said, and what you can do is you can think of the parameter, which is in essence the potential energy of the kinetic energy. If the potential energy is much bigger on average than the kinetic energy, then imagine what that means is that in some sense all the particles, if they're going to move at all, have to move in a very highly correlated way. Whereas if you have a kinetic energy that's really a lot bigger than a potential energy, you have some surface down here, then you just kind of go flying over the top and you just sort of see things on average. So this is a really important parameter. It has the temperature in the denominator. So as you go down from 100 Kelvin to 1 Kelvin, you go from very weakly coupled, where you can think of it as a classical plasma, to something strongly coupled. Another thing that's sort of setting a time scale in this is, for example, the speed of an electron. If you're at 100 Kelvin, the speed is tens of kilometers per second. But remember, the size of the plasma is a few hundred microns. And so the time for the electron, in some sense, to go back and forth across a plasma is measured, in tens of nanoseconds or so. So it's a very fast thing for the electron to go back and forth. Probably the one that hasn't been mentioned, but a very important parameter, is how fast will the plasma thermalize. And so if you have electrons that are made with a laser that is essentially at one energy, then you don't have a Boltzmann distribution. And so it takes a while for, in essence, a spike in velocity to be converted to a Boltzmann distribution. And how long will that take? There's a way of estimating this. In essence, it's the density times V times the average of the Coulomb cross-section gives you a rate. And so if you take that number, for example, for 100 Kelvin and 10 to the 9 per cubic density plasma, you get times of about 64 nanoseconds, much shorter, remember, than the times that they were looking at. And as you get colder, you thermalize even faster. So you might imagine that you'll thermalize very fast, except if this is true, there's something that's still a little bit of a problem, at least when I was thinking about it, is that the electrons can evaporate, and there must be some sort of time scale for that. So if in some sense you can thermalize instantly, then there'll be all these electrons that will be boiling off really fast, and how much energy will you lose to evaporation? That's maybe not something that's quite so obvious. And finally, when we were looking at why I got interested in the ultracold plasmas, is that there were these interesting experiments that seemed to say, well, there's lots of Rydberg states being made with recombination, and at the time, they're really how those Rydberg states were behaving weren't what you would expect from three-body recombination. And it wasn't clear at all what was the mechanism for the recombination. A year ago, I remember Steve Rolston giving a talk, and there's very speculative models for what was causing the recombination at that time. But really, the only thing I knew for making recombination was three-body recombination. And as you just heard, the total rate goes like the temperature to the -9/2 power. So you go from a regime at 100 Kelvin, where essentially you would get no recombination on the few microsecond time scale, to 10 Kelvin, where you would get about 10% recombined in a microsecond, to 1 Kelvin, where everything would be recombined in nanoseconds. So there's something clearly weird that would happen with this as you lower the temperature. So when we went to do the simulations, it was always in our mind that, well, we didn't know what the recombination mechanism would be. We were going to put in this, though, as the first one to try. So the paper that has come out on this was just now a few months old. One of the molecular dynamic simulation was the paper before this, and the week after was the other molecular dynamic simulation. We all came out within a week of each other in PhysRev letters. So I'll tell you a little bit about the theory. I do the simulations two ways. I don't want to do molecular dynamics, so how we're going to do it is at two levels. The complicated level for us will be that we're going to put in the thermalization in some sense by hand by doing Monte Carlo simulations. We'll have the electrons moving around in the mean field of all the other electrons in the ions. And what you do, though, to get how thermalization comes about, and this was something I didn't know because I didn't come from the cooling and trapping community, is that recombination just comes when you have a collision and you rotate the interparticle velocity. And that's all that you really need to get thermalization. And that rotation just comes from the Coulomb cross-section for charged particles. And so we're going to do a molecular dynamic simulation where we put in the electron ion scattering through this rotation mechanism. The ions will move in some sense as a pressureless fluid. They don't really interact with each other. They just see the mean field. And when we do that, it takes about 2 days to run a single simulation on a PC. We'll find that that thermalization actually happens fairly rapidly, so we did go in and do some approximations where we said, well, the electrons are just in a thermal distribution they thermalize so rapidly that we won't worry about the mechanisms for it. And we'll look then at how the things evolve for that. And it's about 2 orders of magnitude in time between these. We also had a much more simplified model, but I won't talk about that today. So just to tell you a little bit about the calculation, what we do is we calculate the mean field for the electrons. We have the electrons just moving by Newton's equations. And then we say if they're within a certain distance of each other, there's a certain probability for the V1 minus V2 for those 2 guys to rotate. We also put in that an electron, in some sense, can hit an ion, and then its velocity vector will just rotate in space by a certain amount. So that also controls how the electron moves through the plasmas. So we put the electron thermalization in. We don't put in the ion thermalization because the time scale for that goes like the ratio of the masses of the ions to the electrons, and this is xenon. So this is a huge ratio. Even though this occurs very fast, the electron-electron thermalization, you would estimate that the electron-ion thermalization takes place on time scales long compared to the experiments. So what we wanted to do was look at the evaporation of the electrons and how much does it cool the plasmas, how cold does the plasma get during this expansion. And when we started to do it, we were doing it with this Monte Carlo calculation, but neither Jim nor I had really experience with it, so we did it 2 ways, one doing the Fokker-Planck equation and one doing the Monte Carlo approximation. And just it's sort of amusing to see how you get a thermal distribution. So what I did was I made a little movie where I have an isotropic distribution, and that's this little solid line. Actually, there's 2 isotropic distributions in space, but they're very, relatively speaking, narrow in velocity space. And this is a Maxwell-Boltzmann distribution, this fat guy. And what I did was 2 simulations, one where we were doing the Monte Carlo simulation where you have the Coulomb scattering to give you thermalization, and one where you do the Fokker-Planck, and they should give you the same answer. When you look at the movie, how does this thermalize with time? And you can see that, at least for short times, they look quite different, but they go over to thermal distribution on roughly the same time scale. And all of the different, I was excited about the difference, and Jim Hansen just kind of slapped me and said, no, this is a trivial difference. It just has to do with the fact that in the Coulomb cross-section, you have large angle scatterings. Whereas in the Fokker-Planck equation, it's inherently a small angle scattering kind of approximation. And so you should expect those sorts of differences. But we did, you can see on a log plot, that even the very high velocity components of the distribution were giving the same result. So we sort of had confidence that we were doing the thermalization properly. Then we started to look at the plasma, and what happens is the plasma is an extended object. It's not isotropic in space. You start out with the same energies in some sense at all points in the plasma, and we looked at, do you go over to thermal distribution on the time scales that you expect? And this is from a full run with a spherical plasma, and in about 45 nanoseconds at 30 Kelvin and 10 to the 9 per cubic centimeter, you get fairly close to a Maxwell distribution. If I showed you a little bit longer, like at 60 nanoseconds or so, they're very close to each other. But one of the neat things that we found, and this is something that was sort of a surprise, was that, and it relates to how do electrons boil off, is that the temperature in the plasma, even though you start them all off, all the electrons the same, the temperature, as calculated by the average of 1/2 mv squared, was different at different distances inside of the plasma from the center. So to show you that, this is from a simulation we did. This red curve is the temperature of the plasma right at the very center of it. You take a little ball and calculate the temperature of the electrons inside that ball. The green is a little shell about 1/4 of the way out in the plasma. The blue is half of the way out, and the purple is 3/4 of the way out. And you see that although the plasma sort of at each little distance might thermalize on this sort of time scale, to get thermal equilibrium, which is you have the same temperature all the way through, it takes a bit longer, although it's still short on the scale of the experiments. This is a microsecond over the whole range. Notice that there is a trend down. It's cooling off, the plasma. So why is that happening? And we did this by accident. When I ran the code one time, I put a 10 to the 7 instead of a 10 to the 5 into the mass. And so I did a run with 100 times larger mass for the ions, and so they essentially couldn't move. And so now the time scale goes from 0 to 6 microseconds. And the red curve is from the center of the plasma, the temperature at the center, and the purple is at the edge. And you see that for both 100 times mass ions and the regular mass, you get thermal equilibrium on about a half a nanosecond time scale. But if you don't let the ions move, the temperature really doesn't change very much at all over 6 microseconds. But if you let the ions move, then the temperature actually dropped by about a factor of 3. And this is just what Tom was telling you, is that because of the electron pressure you're pushing open in the walls, you're cooling the plasma as the electron part of the plasma as it expands. So since everything is in thermal equilibrium, we decided to, put that in by hand as one of our since we'll be able to run it a lot faster. And this is actually, relatively speaking, a very difficult equation to solve. You're solving, this is the ion density, this is the electron density, and you're saying it's in thermal equilibrium, so this is just E to the potential energy over KT. But the potential energy depends on the potential. And so you have to solve this equation to get what the electron density is. It's not as easy as it looks. And when I saw it, it didn't look easy to me. It's actually kind of hard. To show you that the thermal equilibrium ideas work, what I did was look at what the ion density looked like. So this is R squared times the ion density. For a Monte Carlo run in a code where the electrons were in thermal equilibrium, this is 900 nanoseconds after the plasma was created, and you can't hardly see any difference, but it's not fair. The thing hasn't hardly moved. So let's let it go to about 4.5 microseconds, and it's changed actually quite substantially, but you can see that really even this kind of weird feature right here is reproduced in the thermal model. So in some sense, you can say the electrons are in thermal equilibrium. So that was some of the things that we wanted to understand. But one of the things that has to be true for our simulations to make sense is we're assuming that this is a weakly coupled plasma. And the parameters aren't always in the region where the plasma is weakly coupled. So we should always have the potential energy be a lot less than the kinetic energy. And what we found when we did the runs originally, we didn't put in recombination. We found that as the plasma expands, the density is decreasing, so the potential energy is dropping, but the temperature is falling even faster. And so what happens is if you don't put in any three-body recombination, the Coulomb coupling parameter goes shooting up and actually becomes very quickly larger than 1, even if you start at relatively small values of the Coulomb coupling parameter. However, if you put in three-body recombination, that heats up the electrons. And the three-body recombination is more efficient as the temperature drops. And so what happens is even if you start out in a range where the Coulomb coupling parameter might be large, you tend to drop down, and the value that we had for these parameters, which was a plasma starting at about 10 to the 9 per cubic centimeter, and xenon, was we're getting a value of about 1/5 for the Coulomb coupling parameter. So that was important because we're always having a simple plasma.
Francis, did you simulate the three-body recombination, or did you put in that formula T?
No, I put the formula.
Okay.
Not that formula, but the formula that distributes it over Rydberg state. So when you do the recombination, you recombine into a whole distribution of n levels.
States. Okay.
Yeah.
Thanks.
Let's see. Oh, and here's some of the neat things that we learned about this just from doing this. It wasn't obvious to me. I mean, maybe it's obvious to you guys, but I thought it was kind of neat. When you look at the electron and ion density and you plot them on the same graph, you can see a little bit of red peeking out in a couple places, but they're almost the same because it's so cold. The ion density and electron density have to match quite well. So if you take the difference, there's now a 2 order of magnitude difference in the scale of these two guys. So I take the difference. You find that actually there's a region, a fairly large fraction of the plasma has almost constant difference of charge density. And if you remember, I mean, you probably solved this case where you have something spherical with constant density. When you have that case, the potential energy goes up quadratically with the distance. And then kind of a neat thing happens. The ion minus electron density starts out positive, but it drops to a negative number when you get outside the plasma. And that's just because the electrons are so light they can actually kind of get outside, whereas the ions are sort of stuck inside. And so that's why you get a little bit of extra electrons out there. But this was a neat thing that I hadn't thought about before, is that when we went through and calculated the electric field, you find that the electric field goes up linearly, of course, if you have a constant density, out to about some point, and then, of course, it starts dropping like 1 over r squared as you get outside the thing. But when we wanted to understand why was it going up linearly, I realized that there's actually a weird way of thinking about it that makes sense. We were saying that we're in thermal equilibrium. And so the density goes like the potential energy over kT, right? And I always tell the students in like pre-med class, like, well, equations don't go one way. I mean, there isn't a direction to the equation. You can go, in some sense, the other way. Well, you can take the logarithm of this and say, well, the potential energy is kT times the log of the density. But you saw from one of the graphs just a couple times back that the electron density was pretty much equal to the ion density, which I put in as a Gaussian here. So the log of a Gaussian just gives you something that's quadratic, and that's why we were seeing this quadratic dependence. And when you put that simple form in, that's that solid line right there. It just falls on what was actually we were seeing. So that was neat. When we did our runs, we did the calculation. We didn't put in 3-body recombination. We just got that conservation of energy curve that Tom Killian was talking about. When we went and we put in 3-body recombination, we got this little dashed line here. But the results for the 3-body recombination didn't agree with, even though it sort of is agreeing with this expansion of the plasma versus the energy that you input. Even though that's sort of agreeing, the Rydberg physics didn't agree. They looked at the Rydberg atoms, and what they found was that at lower temperatures, the Rydberg atoms were more deeply bound instead of less deeply bound, which is what you would expect from 3-body recombination. They found a density dependence to the Rydberg distribution, which you wouldn't expect from 3-body recombination. So we didn't agree with either of those. And then the realization hit that when you do a 3-body recombination, you make a Rydberg atom. And the Rydberg atom doesn't just disappear, it's still sitting in the plasma. And a Rydberg atom, this was a whopping big Rydberg atom, and the electrons can collide with it. And typically what it does then is de-excite the Rydberg atom. And so when we put that mechanism in, we really got agreement. That's the dashed line up there that's in the best agreement with their velocity. But we also got agreement with how their Rydberg distributions behaved. When we didn't put in the electron-Rydberg collision, we had a huge amount of 3-body recombination, which really wasn't being seen. And so when we did this, we got fewer recombination because every recombination didn't just give you the recombination energy, it also sort of gave you all the future de-excitation energies that came with it as well. We tended to get more deeply bound Rydberg atoms as the temperature of the plasma dropped instead of the reverse, because the plasma expanded more slowly at lower temperatures, which gave the electrons more chance to hit the Rydberg atom and de-excite it. we also found more deeply bound Rydberg atoms at higher densities, again, because of this mechanism, you could de-excite it. Just to show you some of the other things that we've done, just to convince you that we kind of understand a little bit about what's going on in the plasma. One of the things that you saw is that this is a little bit of a change of pace. This is now looking at the electron coming out of the plasma versus time. This was one of the first kinds of signals that Tom was looking at in the cold plasmas, is that what happens is after you do the photoionization of the cold atoms, you get a burst of electrons coming out. And then if you look carefully, there was sort of a slower decay of electrons coming out with time. And one of the neat things about this is that you know the plasma densities, you know the energies fairly well, and so in principle we should be able to compare them, you know, really in detail, what a calculation would give of the electrons coming out versus time, and compare it with the experiment. And that's what this graph is. The dashed line was some unpublished experimental results from Jake Roberts, who's at NIST right now, showing the flux of electrons coming out of a relatively cold plasma as a function of time. And the solid line is a calculation of it. It's actually a little bit better than it looks, because there's a couple of things that you need to do to get this agreement. One is that this first peak was broadened out a little bit, and so we convolved the calculation with about a 200 nanosecond, which is just 2 tick marks on this thing, a 200 nanosecond width. So we had to change the width a little bit by convolution. The experiment has been shifted by about that much in time because they said there's a little bit of uncertainty of how long it takes the electrons to actually get to the detector where it's being detected. And we also changed the size a little bit of the overall size of the curve. But all of those changes were within the experimental uncertainty. But if you think about it, then there isn't that much left. There are a couple of things. We're getting the ratio of these things correct. So there's no fiddling with relative things as a function of time. So we're getting how much prompt electrons are coming out versus how much are kind of leaking out later. Another thing that we're getting is there really isn't any fit on this side. And this is a broad thing. And so how the rate that stuff is going out is decreasing slowly, and we're getting that right as well. So how the thermalization is occurring is, I think, being described well. Just as another thing, I can just show you that this was one of the mysterious measurements that they had, is that at 100 Kelvin temperature, they would see more deeply bound Rydbergs. This is the number of Rydbergs as a function, essentially, of binding energy going this way. 100 Kelvin plasmas gave more deeply bound things than 200 Kelvin plasmas. When I do a simulation with really the same sort of parameters, you see really the same kind of structure. 100 Kelvin guy is tends to give more deeply bound Rydbergs than a 200 Kelvin guy. Finally, there is this very strange insert to one of their figures where they looked at the number of Rydberg atoms they had as a function of time. And so the solid line is the density that they were estimating of their plasma as a function of time. And this is their number of Rydbergs. Now, it turns out for technical reasons, I can't do exactly these same parameters, but I can get close. If I'm at 6 Kelvin and they were at 10 to the 10 per cubic centimeter, as I did at 10 to the 9 per cubic centimeter, I find that the number of Rydberg atoms drops and then increases in a very, very similar sort of way as here. The scales are messed up a little bit because of the different densities, but I think otherwise everything looks great. And why is it? I mean, this is very strange. But when you do the calculation, it's very clear what happens. Initially, you start out at 6 Kelvin. Now, in the experiment, you start out at 6 Kelvin, but you have to remember when they're saying they're detecting Rydberg atoms, that means they're detecting Rydberg atoms above n equals 40 or so, right? Now what happens is the plasma immediately almost heats up, and that drives the range of allowed bound Rydberg atoms actually below the region where they can detect. So in some sense, the amount of Rydberg atoms that they could possibly detect has gone to 0 because the plasma is heated up. And then the plasma starts cooling off and you start making more Rydberg atoms. If you could actually measure all the Rydberg atoms, you would just find it going up. But if you look above n equals 40, you see this very sharp drop and then slower increase at later times. Let me just show you one last thing and we'll call it a day, although I have some neat things with the ion acoustic waves. We talked about the plasma expanding, the ions moving and stuff. So I decided let's make a movie of that one time. And let's look at the ions expanding. So this is, you're starting out at 10 to the 9 per cubic centimeter, 30 Kelvin for the electrons. And the average, the square root of r squared was like 340 microns. And so let's run it to show you how the plasma expands. And of course what happens is initially it doesn't move very much because you have to have velocity first, and then you start getting velocity and the thing expands, and this weird thing comes in. And you get this spike way out here. Well, what is that? And when I saw that, I said, this is really cool. This is neat. And this is, I'll show you again. It's kind of cool. I kind of like this little movie. I mean, it starts out as a Gaussian, and then you kind of see this shoulder comes in, and then you get this spike coming in right on the edge. Very strange. And I can blow it up. It happens over a very short time scale where you go from just kind of a little shoulder thing to a spike. This is 6.3 microseconds, and this is about 7 microseconds right there. Where is it? It turns out that this is a very common plasma phenomenon if you're expanding into vacuum. If you remember this curve, I said that, well, the electric field is going up linearly, then it drops like 1 over r squared. Well, everything starts out at 0 velocity. So imagine that we set up a race where what we're going to do is for this sort of region, we'll put the faster guys out in front. Well, they'll just keep, leaving the slow guys behind. But out here, we have the slow guys out front. And so what will happen is the fast guys will catch up to them. And when they catch up to them, it's when you get that spike. And to show you that that's really what happened, I plotted on here both the velocity of the ions as a function of distance and the density. And you can see that there's two spots. This is where the fast guys have caught up with the slow guys and actually have passed them a little bit. And you can see actually 2 spikes. You get a spike every time dV/dr goes to 0. So with that, I can show you ion acoustic waves. But let me finish up and just tell you what I think that we've learned from this. One thing is that it's really a classic plasma. The atomic physics is, in some sense, simple atomic physics, well-known atomic physics. But both the plasma physics and the atomic physics, in some sense, have to be treated right and done with equal amounts of seriousness. Otherwise, you don't really get what's going on. It's the three-body recombination. We're very firm about that. That's the mechanism that's for making the Rydberg atoms, things like some of the other mechanisms that have been discussed, I don't believe in. Well, I told you about the more deeply bound guys and some of this stuff. Let me just tell you, I think, some predictions in the future. We think that all of plasma physics, because of this recombination, instantly heats things up, that the plasma physics will vary smoothly as you go down to 0 energy. And even a little bit below. One thing is that the velocity of the Rydberg atom does depend on the velocity of the ion when it recombines, so you should have some relationship between binding energy and velocity of the Rydberg atom. And I see that in the simulations. I'm not sure if you could ever see it experimentally because of the range of Rydbergs that you can see. But I definitely see that. We should see the plasmas go over to simple plasmas, which means that you heat. There's some neat things for the future, some precise comparisons between experiments and simulations. I like to look at some different geometries, things like ion acoustics wave, and see if this expansion into the vacuum is there. And I'll finish up and just leave this up. Here's some references of the work that's been done. Thank you.